Okay, let's try this again. I made this video earlier and apparently the recording quit midstream, so I didn't even do more than 2 or 3 minutes of a talk. But now I've practiced and this should be better. So we're going to talk about coordinate systems because these next 2 weeks we're going to work in different coordinate systems. So just so we have a frame of reference, let's recall what we've been doing forever. We work generally in what are called rectangular coordinates. And points are labeled x comma y, right? So we have this graph paper. And so the plane is actually cut into little squares. And as we saw with area, if you look at the area differential, it's dx dy or dy dx. And so what we're adding up to find area are these little boxes with width delta x and height delta y, and then in the continuous case you have dx dy. So that's the area differential in rectangular coordinates. And when you're going from the origin to some rectangular coordinate, you go horizontally and then up, right? And think of it as a chess move. The only way you can go is left and right and up and down, okay? To actually travel diagonally, you have to go first this way and then that way, or first that way and that way. So, rectangular coordinates. I run this course differently because I like to, and I've seen enough problems in the past. So the second coordinate system we look at are polar coordinates. Now, some of my fondest memories of teaching high school math are working in polars and cylindrical and sphere coordinates, which we're going to do now. But this is supposed to be a review, but probably many of you haven't seen it, so it's probably an intro. Or if you have seen it before, you're probably rusty because they probably only did it for a day. The polar coordinates have a different, instead of having points x comma y, they have points r comma theta, where r is the distance from the pole, i.e. the origin, and theta is rotation. Okay, and so I put a little work into this because I'm so into it. And here we go. If you go online anywhere, you won't need these for class unless you're like me. This is a polar coordinate graph, right? And so if we wanted to graph the point 2 comma pi over 6, go away. You would start here and you'd go 2 units out to here, and then you rotate pi over 6. So that's pi over 6. It's pi over 4. It's pi over 3. So you'd rotate, and there's your point there, 2 comma pi over 6. Right. Okay, and so now instead of having fundamental regions that are squares, we have fundamental regions that are these little sectors. And that's what they're called. They're sectors of a circle. And in the sequel, either in this video or the next one, we'll fiddle around with this guy at length, because that's how you get your area differential in polars. But for now, let's just make sure I'm still recording. I am. So for now, let's just look at polar coordinates for a minute. Do some fun stuff here. If I take the equation r equals 1 in polar coordinates, that gives me what? A circle. All right? Because theta is free. So the distance from O is always 1, and you just let theta go around, so this is the unit circle. Right? So in polar coordinates, this is how you represent the unit circle. And in rectangular coordinates, that's how you represent the unit circle. So you see, we already see a simplification here. Okay. Similarly, if you look at the equation theta equals pi over 3, then r is free. So what is this? This is a line. So this is a line in polar coordinates. A line through the origin in the direction of pi over 3. Right? And if you come over here, let y equal 1, you get a line horizontally like that. Okay. All right, so let's do this. I'm going to get another piece of this graph paper. Okay. And I'm going to impose the XY plane on here, okay? And then I'm going to just pick a random point out here, right? And so this has got what it's got. This length is r, and this rotation is theta. That's how you get to this point, r theta. And we'll use black for the xy. If I want to get to here, this is the point x comma y. I go this way, and then this way, and this is x, and this is y. And it's clear that they have a lovely relationship. That is that x squared plus y squared equals r squared. All right? So this is something we use a lot. It's also true if you use sines and cosines that x is equal to r cos theta and y is equal to r sine theta. If you just think about this, the sine of theta is y over r, so you solve for y. The cosine of theta is x over r, so you solve for x. And similarly, tan of theta is y over x. So these are identities that we use to convert from polar to rectangular, assuming you need to do that, which we will. Okay. So this is about where I figured out last time I wasn't recording, and now I see that I am, so that's good news for me. Okay. So let's find the polar equation for the circle x squared plus y minus 3 squared equals 9. And this is a circle of radius 3 centered at 0, 3. So let's see, it looks like this. Okay, so we're going to use those identities here. Foiling. Okay, and then you see that this guy is r squared, and this guy is r sine theta. Just using those identities. Factor an r out, and you have r minus 6 sine theta equals 0. So this says either r equals 0 or r minus 6 sine theta equals 0. And so solving this, you get r equals 6 sine theta. Okay. And if you have a graphing calculator and Desmos, and I think GeoGebra, they all handle polar coordinates as well. Okay, so that's a little intro to polar coordinates. And now I'm gonna do some calculus here. Okay, so note. We have been doing double integrals over some region R, some function f of x, y, and we use dA for our area differential, right? And this is in polar coordinates. Sorry, rectangular coordinates. Okay. Now, if you don't have to write this next bit out, just let me write for a minute here, and then just follow. Okay. So let's say we're given this guy. And so we have dy dx. And if you look at this thing, it's the region R is a semicircle here. So here's the region R, and this function above it is what? It's one of those paraboloids, I think. Yeah. Doesn't matter. Let's do some integrations, right? So in the first round, when you integrate, you get x squared y plus y cubed over 3 evaluated from 0 to 1 minus x squared, and now you're left with dx. Okay, so you just keep going, or I'll keep going, you watch. This is, when you plug in the upper bound, it's x squared times the square root of 1 minus I squared minus 1 minus x squared cubed over 3. Now, sorry, to the 1/3. 3 halves, duh, sorry. Doesn't matter, because now you're in little hell. And there is a way to solve this, and it's going to take you half an hour, but trust me, if you convert this to polar coordinates, it's a one-liner. I'm not going to do that now because that's not the point of this. The point is to build up to being able to do this, which will happen either next week. So, but I do want to get started on how we find our area differential in polar coordinates. Now, I love this next bit. I know if we were in class, you might start having a panic attack. Just follow along, take as many notes as you want, or just enjoy it. I can't not do this though, because there's an end result that's minor, and for years people have always said, where does blank come from? And you can't just go, oh, it comes from this one little thing. It comes from all of this. And so, okay, let's do this. I'm going to get up another piece of paper. That was the best move I made today, besides my workout. Okay, here we go. So in rectangular coordinates, we're adding up dx times dy, little squares. And in polars, we're adding up these. Let me make this really big. Oh, yes. Okay. We're adding up these things, which are little sectors of a circle. Okay, they're not quite rectangular, which makes this fun. Okay, so here's what's going to happen. I'm going to set this up. Okay, So we want to find the, sorry, I don't want that much. So this is theta equals alpha, and this is theta equals beta. So those are my upper and lower bounds of this thing, and we want to find the Riemann sum for this thing. So we have to find some little a sub k here, okay? So that we can add them up. So we have 1 through n, and then you take the limit as n goes to infinity, all that. So the whole thing that this is about is getting a handle on how to compute this little differential a sub k, which will give us dA. All right. So here's the deal. Let me erase that. Here's the deal. Somewhere inside here is a point, rk theta k. I'm just going to leave the r there. So this distance here is delta theta. That's the opening. And this distance here is delta r. And again, it would be nice if you could just say it's delta theta times delta r, but this isn't a rectangle. Okay? It's curved here and here, right? Because it's on a circle. Okay, so we want to find the area of this wedge. This comes from geometry. Okay. The area of a sector is 1/2 theta r squared. So if I was finding the entire area of this sector here, so this whole big sector here, it would be whatever this theta is times whatever r is squared, 1/2 that. We're just trying to find this little guy here. All right, so what I'm going to do now is shut this for a second. Come down here, come on. And I'm going to expand that thing. So what it is this guy, it's about that big. Okay. Here's the point RK. This I said was delta theta, and this was delta R. So back down here somewhere is the origin, right? So first, to find this area, we want to find the area of the big sector. Can I go back up here? Yes. I want to find the area of the big sector and then subtract the area of the little sector, right? That's all we're doing. Okay. Okay, so what is this distance here? Because this is the big sector. Well, if this is RK, which it is, this is RK plus delta R over 2. That's this guy here, right? Because all I've done is taken half of delta R and added it to get to this length. And so this guy is RK minus delta R over 2. Okay. And so so again, this distance is that, and then this distance is that. So we're going to look at the difference of the two, right? So a sub k is going to be 1/2 theta. Sorry. Right, better pull man. 1/2. So theta is actually delta theta. And then we have the upper radius, which is R of k plus delta R over 2 squared minus R of k minus delta R over 2 squared. right? So all we've done is plug in to this formula our first term and our second term. And now you do the obvious algebra. So we have RK squared plus delta R RK, doing the insides, plus delta R over 2 squared minus RK squared minus delta R RK plus delta R over 2 squared. All right? And this becomes 1/2 delta theta. And this is nice. Those cancel. Those cancel. And we get 2 delta R RK. And this cleans up nicely. We get RK times delta R delta theta. All right. And so this is AK. This is the area of one of these fundamental regions in our Riemann sum. Right? So now we set up the sum. It's the sum from k equals 1 down to n. And let's assume there's a function. And now we have our differential, RK delta R delta theta. And when you take the integral of this guy, when you take the limit, you get what's called a double sum because of the delta R delta theta. And so theta runs from alpha to beta. R runs from some function of theta to another function of theta. And you got the function f of r theta times dA, which is r dr d theta. Okay, and that's the differential in polar coordinates. Now, and just so I'm clear, will I make you reproduce this? Probably not. But what we do know is that for some reason that work caused us to pick up an R here in the differential. So coming full circle in rectangular coordinates, we have R f of xy dA, where dA is either dx dy or dy dx. Doesn't matter. And now we have R f of r theta dA, but dA is r dr d theta. And what you'll find when you do these problems, which I think is cool, this R saves your life so many times because you wind up with some sort of U substitution and you want an R to be out front of an integral or a radical or a square root or something, or a third, and there it is. It saves you over and over and over and over again. Okay, so as we move forward into integrating with respect to these different coordinate systems, just remember that it's the same thing every time. It's a double integral over some area, and that gives us the volume piece, dA, and dA is dictated by which coordinate system you're using. And just so we're clear, we're using rectangular, polar, spherical, and cylindrical. So in the end, there's going to be 4 different coordinate systems. And this is our first sort of it's our first non-rectangular system, the polars, which I love because, well, I digress, but I'm going to. I need to find this thing. And the reason I'm bringing this one up is because a student, what did he do? He earlier in the semester, a student copied something down wrong and wound up graphing in polars, and he got one of these. There's cool names like the cardioid and a four-leaved rose and a dimpled, what the hell is that? A dimpled limescone and a limescone with an inner loop. There's oval limescones. There's a thing called a nephroid of Freeth. Oh my God, we have to do that. Here it is. Forget about this. That's too easy. 1 plus 2 sine theta over 2. Unfortunately, it's got a t next to it in your book, so that means you have to use a calculator. I still think we can do it by hand. It's called a nephroid of Freeth. So it asks us to graph the nephroid of Freeth. All right, I'm running out of time, so let's see how good. Where's Desmos here? Oh. What did I say it was? 1 plus 2. Where are the functions? Sine. All right, here's where you got to be careful because you want to put in theta. Let's see if it just works straight away. Nope. Maybe. Ah! I hope this works. It did. There is a nephroid of Freeth. Pretty cool. If you can figure out how to use that in a sentence or where it's from. Let's fool around with this for a second. Let's go from 0 to pi. Where's the division over here? Over 2. Yeah, so we could graph this by hand. It wouldn't be that hard. You just have to make. Oop, something's wrong. That's not it. It's supposed to be. Hold on. Theta over 2. And that should be 2. Where's pi? Pi should be here somewhere. There's multiplication. I just type it in. There you go. It looks like a balloon that's been shot or something. All right, here's the entrance. Oop, I can't write on this. So, anyways, yes, and we will be able to find out the area underneath the curve here using integration next Wednesday. All right, I hope you enjoyed that. See you in a bit.